In this video, we want to learn what kinds of information we can learn from our exponential models. We'll start with this situation. In 2007, the world population was about 6.6 billion, and it was estimated that the population was increasing by 1.36% every year. What model describes this situation? If I let P of t be the population in billions, then the population after t years is the 6.6 initial value, which represents 6.6 billion, times a growth factor of 1.0136 to the power t. I get this growth factor using the fact that the growth factor should be 1 plus the growth rate of 0.0136. That's our 1.36% growth every year. So with that model in hand, you can use it to make a prediction about what the population might be in a different year. The year 2015 corresponds to t equals 8, because our definition of t was the number of years since 2007. So if I know the value of t is equal to 8, I can simply substitute that into my model and come up with about 7.35 billion as the population for that year. Another question we might ask is when the population will double. Last time we were given a certain year and asked to evaluate what the population would be. This time we know the value of the population should be about 13.2, because that's double of our initial 6.6 billion, and we want to know at what year that happens. That's a more complicated question to answer. One way to estimate it would be to plot the graph of our model, which I have here in blue, and then I just have a guideline at y equals 13.2. Where these two lines intersect represents the point where the population is 13.2 billion. From the graph, it looks like it's a little bit bigger than 50, so we might estimate something like the year 2057. An algebraic approach would be to ask, at what value of t is the population model equal to 13.2? And we know the definition of the model, and now I need to isolate t. So I might begin by dividing both sides by the 6.6, and notice the right-hand side is a 2, which we expect. Another way we might have asked the question is, how long before the growth factor behaves like 2? And this is what this last line says. Now I have the situation where the variable I'm interested in is in the exponent. Logarithms are precisely the tool we need to remove items from the exponent. So if I take the logarithm of both sides, the left-hand side becomes t times the logarithm of 1.0136. This is the power rule of logarithms we saw when we were talking about logarithm laws. I could isolate t by dividing both sides by the log of 1.0136. If I plug this all into my calculator, I get a value of t around 51.31. So the algebraic approach gave us a slightly better estimate that the population will have doubled in the year 2058. While we're looking at this problem, I recommend that you save all your rounding till the very end if possible. For example, here it would be tempting to evaluate logarithm of 2 and round, and evaluate the log of 1.0136 and round to make the equation look simpler. But by rounding twice, we've introduced more error. And in fact, when we divide to isolate t, we'll introduce yet more error. If instead we write our answer in this way, we round only one time. We type all of these logarithms and the division into the calculator at once, and we get just one instance of rounding. We get slightly better accuracy this way. If we are interested in checking that our estimate was right, we could plug in our value of t, which was 51.31, and see that the model gives a population of just about 13.2, which is what we expected. This example has nothing to do with the population model, but I wanted to show that we can use our laws of logarithms to solve logarithmic equations as well. If the equation is rather complicated, we might just use a graphical estimate as we did before. We can plot the equation natural log of 2x plus 1 minus natural log of x, and that's in blue. And then I can plot the line y equals 2 just as a guideline to help me see where the intersection is. So that equation is equal to 2 right where the intersection occurs. So the x value that corresponds to that intersection is about 0.19. This equation is simple enough, however, that we can use the laws of logarithms to solve it algebraically. I could use the division law to turn the difference of two logarithms into the quotient of a single logarithm. Now that I have everything as just one logarithm, I'd like to cancel the log. So I write e to the left-hand side of the equation is equal to e to the right-hand side of the equation. The left-hand side, the e and log cancel, and I'm left with 2x plus 1 over x. And on the right-hand side, I've evaluated the e squared in my calculator and rounded it to 7.39. Here, I'm not exactly following my own advice to keep as much accuracy as possible. It might be better to leave this as e squared for as long as possible, but I don't think we'll see much difference in this example. Since I have an x in the denominator of the left-hand side, multiplying both sides by x would be a good choice to make a simpler left-hand side. Then I can subtract 2x from both sides to gather up all the x's. And finally, dividing both sides by 5.39 would isolate x at a value of about 0.186, which is very close to our visual estimate of 0.19. As always, if I want to check this answer, I can take an x value of 0.186 and plug it into the original equation. It comes out to about 2. Since we rounded the e squared, we introduced a little bit of error.